Hello, I'm Eric, and let's talk about engineering. Memo story progress, Thread 1.4 eliminates silos between Apple, Google, and Amazon, creating a unique IPv6 infrastructure and reducing NFF failures in the IoT ecosystem through standardized sharing of credentials and network routes. Unification of Thread 1.4. From my perspective as a senior engineering program manager, the evolution of wireless communication protocols is not just about better speeds, but about systemic robustness and operational reliability. For years, the smart home and industrial IoT ecosystem based on Thread suffered from fragmentation reminiscent of the worst days of driver incompatibilities in the 90s. We had border routers from Apple, Google, and Amazon operating in the same physical space but creating isolated connectivity islands. For an engineer, this is an unacceptable inefficiency, multiple meshes competing for the same spectrum, without cross-redundancy, exponentially increasing points of failure. The arrival of the Thread 1.4 specification changes the game by standardizing how these devices share network credentials and routes, allowing an end node to see a coherent and unique IPv6 infrastructure regardless of which brand manufactured the gateway. In my experience managing manufacturing and QA projects, one of the most frustrating indicators is NFF, no fault found. At Rainbird, we managed to reduce returns by 20% by tackling precisely the root causes that were not evident in the hardware. In the IoT context, NFF often occurs when a sensor disconnects because its specific border router enters a zombie state or loses cloud connection, even though there are 3 other functional border routers just meters away. With Thread 1.4, a secure and standardized credential transport layer is introduced that allows the formation of a single network partition. This means that if the Apple border router fails, nodes can reroute their traffic through a Google or Amazon device transparently. From the DFMEA, Design Failure Mode and Effects Analysis, perspective, we are eliminating critical failure modes related to infrastructure availability, resulting in higher customer satisfaction and lower technical support costs. Diving into the technical specifications that interest us electronics engineers, Thread 1.4 optimizes the use of IPv6 by allowing border routers to publish prefixes and routes so that end devices can make smarter routing decisions. We no longer depend on proprietary implementations for commissioning new devices. The standard now defines clear interfaces for mobile applications to inject credentials into the mesh universally. Additionally, the improvement in power management for end devices, sleepy end devices, is remarkable, as mesh unification reduces unnecessary network chatter and retransmissions caused by interference between overlapping thread networks. As someone who has worked with ARM microcontrollers and complex firmware stacks, I see in Thread 1.4 the maturity the protocol needed to be truly scalable in industrial and commercial environments where reliability is not optional. For engineering leaders and PMs, the lesson here is clear: interoperability is not just a marketing feature, it is a reliability requirement. By unifying border routers, Thread 1.4 allows us to focus on innovating the application layer, Matter, instead of wasting time solving low-level connectivity issues. In my years at Legrand and other world-class companies, I always pushed for open standards because I know hardware is only as good as the network that supports it. Thread 1.4 is the backbone that finally fulfills the promise of a resilient mesh, eliminating the logistical nightmare of managing multiple ecosystems and ensuring system uptime is the norm, not the exception. It is, essentially, engineering applied to solving systemic frictions.